All right, I want us to talk about the reactions of alkenes. But to start off, before we even get to any organic chemistry, I want us just to be reminded about a very simple reaction, and that is what happens when water is added to a strong acid such as sulfuric acid. Now, you should know your chemistry pretty well here, so you should realize that this is an equilibrium that lies fully towards the right, where we would end up with the hydronium. So I'm going to draw it like that. Which will be positively charged, and the hydrogen sulfate anion that looks like this, which is our conjugate base, like that. Now, what's happening in this reaction over here is what I want to show you is the way that organic chemists would show this when we're using our reaction mechanism. So the water, in this case, is the base, and the sulfuric acid is the acid, and water, of course, is not a good base. But what we would do is we would show the lone pair of electrons donating their electrons to the proton like that over there. So they're going to be forming a new bond. And then this sigma bond between the oxygen and the hydrogen needs to break, and the electrons end up on the oxygen like that over there. We can indicate these by showing this purple curly arrow that we've drawn over there ends up and forms this bond that's sitting over there. And this green curly arrow that's over here has taken those electrons that ended up on the oxygen, and they're effectively contained in that minus sign over there, which is also the equivalent of an extra lone pair. We could draw out the lone pairs on this oxygen. There were 2 over there. Now that this bond has broken, there are actually 3 around that oxygen over there. And that's something that you see in all kinds of oxygens that have a negative charge on them. And obviously on the hydronium over here, we've only got 1 set of lone pairs which are remaining, that one over there, and we're left with that. Okay, now up to this point over here, in terms of acids and bases, you would call the water the base. I know it's not a good base in any way, shape, or form, but we call this the base and we call this the acid, and that would give us the conjugate acid and the conjugate base. Now, in organic chemistry, we have different words for exactly the same thing. It's just that when we're talking about reactions that are forming carbon and hydrogen bonds, etc., we use these words. And the one word that we'd use instead of base, we use the word nucleophile. Phile means loving. You see that in lots of words. I'm a chocolate phile. And in the nuclear part is the thing that it's saying that it's it's nucleus loving. So what we've got here, and nucleophiles, we're going to see lots of different examples of them, but one of the most common is lone pairs of electrons on heteroatoms, so oxygen, nitrogen, sulfur, etc. So lone pairs of electrons are great nucleophiles because those are electrons that are available to be given to a nucleus. In this case, the nucleus is a hydrogen, the simplest thing that you can add to. And we would call this, of course, the proton. This is the base. This is the acid. And in the nomenclature or the language of organic chemistry, call this the electrophile. So I'm just going to use those 2 colors to try and be consistent. Bases we often just keep to blue, and acids we keep as red. Nucleophiles will be in blue, and electrophiles will be in red as well. So a key skill right at the beginning is going to be able to identify nucleophiles and electrophiles in organic reactions. Before we can do anything, we've got to be able to pick those out. We're going to scaffold this as we go through all the reactions that we do. I'm not going to introduce them all to you right now, other than to say one of the first things to be looking out for with nucleophiles are lone pairs. And the second thing that we need to look out for, and this is where we're going to get into the context of alkene reactions, is pi bonds. There's another one that we're going to be looking at, not right now, will come up later on, but right now I want to focus in on the pi bond. So any kind of, remember, we've got an example over here of water that's picking up that proton. Maybe that wasn't water, maybe it was an alcohol, such as ethanol. The same sort of reaction would happen because alcohols are just organic versions of water. But I want to focus on, let's keeping the electrophile the same. We're going to work out later on, and we're going to see there's lots of other different types of electrophiles. But right now, I want to just keep the electrophile the same, which is to say I just want to have a strong acid present for this. So I'm going to take a very simple example over here of an alkene, and I'm going to make it into a 5-membered alkene, but just for the sake of this example that I'm going to do right now, I want to draw out the two sets of electrons, should I say, that form part of the pi bond. So this molecule over here in our skeletal structure would just be cyclopentene. Okay, that's all we have over there. And I've drawn it out by showing out the Lewis dot structure of that. Now, what I've told you is that pi bonds are weakly nucleophilic. And, well, I told you they were nucleophilic. What I didn't say, of course, was that they're actually weakly nucleophilic. And that is actually quite important. These are not strong nucleophiles in any way, shape, or form, but they are weak nucleophiles. So this pi bond that we have is a weak nucleophile. And so I want us to consider for a moment just what might happen if, and I'm just going to take two of these over there, two of them, to represent that pi bond. Okay, I could have taken any two. I just randomly chose that. Let's consider what happens if we stick a strong acid in the solution. So here we have our electrophile, and here we've got our weak nucleophile. Now let's just think about what might happen if the nucleophile is something that would give its electrons to the electrophile. Let's show what happens if that set of electrons were to give the electrons to the proton over there. What would be the consequence of that? What would that look like afterwards? We can draw that out. So now the two electrons have disappeared, so we've only got one electron left, as in a sigma bond. And the H that came has now added to the one carbon atom over there. So there's the H that was there. And here, just because these electrons were in blue, I'm just going to put that line over there. That is the new bond that has formed between the carbon and the hydrogen. So what we got over here is something that looks like this in skeletal structure, would just look like this over here. Well, not entirely. All right, because this over here would be cyclopentane, and its molecular formula would be C5H10, 2,4,6,8,10. But I want to notice over here that when this happened, when those electrons were given away to that proton over there, notice that this carbon over here now only has 3 bonds to it. 1, 2, 3. And so this bond is no longer neutral. It is actually positively charged. Because it only owns 3 of the 4 that it would like to own. So it's got 1 less electron than it should have. And so it is positively charged. In other words, it looks like that. And a positively charged carbon has a very special name. It's called a carbocation. I've heard students say to me that this is a carbocation. Please don't do that ever. It is a carbocation. And notice that I've done something very, very sneaky here, but intentional, and that is that I have made the carbocation in this pink highlight because when you notice here, the carbocation is missing electrons. It can accept electrons, just like a proton can accept electrons. It has an empty orbital now. It wants to get to its octet. It doesn't want to be positively charged. And so this carbocation can now accept electrons from something else. In this case over here, the acid that I'm going to use, I'm not going to use sulfuric acid because in terms of reactions, it doesn't work very well using sulfuric acid. We'll get to that. I'm going to be using Br minus, okay, as the nucleophile. So we will change this up over here slightly. I'm going to fix it up because initially we don't get HBr is not an ionic molecule. That's not how it goes. So there's no minuses or pluses. It was a bond like that, HBr. And then this bond would have broken so that we ended up with a Br minus. So on this side over here, we now have a Br minus. Br minus, lone pair. Bromine has 4 lone pairs all around it. The bromide, anion, has got 4 of those. And now we've got an electrophile, we've got a nucleophile. Those 2 electrons can add to that carbon over there and generate the final product, which is this. So notice what happened over here. The electrons, okay, the first set of electrons that bonded to that H came from the pi bond. They went onto the H. That gave bromine. Bromine has now electrons that it can add to the carbocation that was formed. All right, so there's the bond that was formed, and there's the bromine over there. Now, what I've drawn over here, we are going to have to upgrade our ability to draw these mechanisms. I've done this specifically to be super explicit about everything that's where all these electrons are, to follow them. But we need to be able to move to just using skeletal structure. So in other words, we take this skeletal structure over here. What happens is that the electrons add to the bromine, it breaks like that, and that gives us this over here. Now notice that what I've drawn over here after I did this is I actually added an H. So I didn't draw the H. The H ended up over here, and this ended up being the carbocation over here. So I didn't draw the H's in. That's totally fine. If you want to draw the H's in, you can, but please be very careful when doing that, because if you put an H over here, you really need to put on both H's. If you put just one H, it means that you're telling me that there's only one H on this, and then therefore that would only have 3 bonds, and therefore it would also be a carbocation. So typically we wouldn't actually show the hydrogen that has been added because it's hydrogen. We don't show it on skeletal structures. But we ended up with a carbocation over here, and this added to the carbocation like that. The electron started at this minus or on the bromine and ended up on this carbon over there, giving us the final product, which looks like this. All right, so these structures over here are what an expert organic chemist would draw out when drawing out a mechanism for the addition of HBr onto an alkene. And this is where all the electrons add and where they go, using the concepts of nucleophile and electrophile. All right, I want to talk about regioselectivity. For those of you who were sharp in the last example that I did, which is very similar, we're just using HCl, is that when I did this reaction, so the same thing will happen for HCl, all right? When I did this reaction, I just went like this, and I very simply put the positive, the carbocation over there, and then we showed the nucleophile coming in, boom, 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 and we get our product where the chlorine ended up on this carbon atom over here. Okay, the question, of course, was, well, why did you do that, Prof. Arnott? What was the reason? I mean, why did you put the proton there on this carbon and not on this carbon over there? In other words, so that the carbocation was actually over there. I mean, if you think about it, there's no reason why it shouldn't have happened. Why could it not, if I just drew it this way, ended up with a carbocation on that position over there? Now, if you did have that question in your head, which was a good one, hopefully you can see that after I've drawn it, well, these two things are exactly the same. All right. We just have to turn this slightly and you will end up with exactly the same thing. So choosing which carbon the proton went onto was actually kind of meaningless. What happens though if we have a molecule which is now unsymmetrical? This is symmetrical, right? You can draw a line through it and either side is exactly the same. So let's just take a very, very simple example of butene over there. Now, if I take butene and I added so I'm going to use a different one now. I'm going to use HI, just again to be different. So we've got HI, and I want to take that pi bond and do the reaction. So the pi bond, I can highlight it, it's going to be our nucleophile, proton is our electrophile. So it's going to pick up that proton like that, and we're going to kick out the iodine. So when that happens, there are actually now, this time, there are actually two possibilities of where that proton goes. If the proton goes to the end over there, there are two hydrogens there already, but if that proton goes on there, we would end up with three hydrogens on there, one new hydrogen and one that was old. So we've got a new hydrogen that's added on over there, and the other two are were there in the first place. And this carbon over here has one hydrogen on it. I'm going to draw it out, all right, just to be explicit here, and that means that that ends up being the carbocation. We have that. There's another option, and that is when the H actually goes over here and the carbocation then ends up on the end. So we can draw that out. So we get this. There's the original H. There's the new H. Color it in. But over here, we've only got the original two hydrogens, which are at the end of this alkene over there. And so the consequence is the carbocation is on this carbon over here. For my head, I hate seeing all these H's. It kind of messes things up. When I draw this out, if I'm drawing out the mechanism like this, what I draw out is there are two possibilities. The one looks like that. There's four carbons. The carbocation is on this carbon over here. And this also has four carbons, and the carbocation is at the end of the chain like that. That's how we should draw things out in our standard skeletal structures. So now the iodine that was remaining, which is now the iodide, it's an I minus, which is our nucleophile. So we've got a carbocation, positively charged, and I minus. When this reacts, we're actually ending up with two possible answers. So that goes to there, that goes to there. We're either going to get something that looks like this, there's the iodine, or we're going to get this over there. All right, and this is there's that new bond in both cases that's formed. You must be able to see that. Now, when this happens, you might look at this and say, okay, well, is it 50-50? Which side it goes to? And it turns out it's not 50-50. The favored product is this over here. So the favored product is the secondary iodide, and this one over here is disfavored. Now, I don't know the exact split for this reaction. I don't know like percentage-wise what this is. That's not important. Rather, it's to know which one will be the major product or favored, and which one will be the minor product or the disfavored product in this reaction. And the reason for this was worked out by someone whose name was Markovnikov. And this is known as Markovnikov's rule. I really hope I spelled his name correctly. So Markovnikov basically postulated that the reason for this major versus minor product had to do with the stability of the intermediates. In other words, this carbocation over here was more stable than this carbocation over here. So the more stable carbocation ends up giving the major product, and the least stable carbocation ends up giving the least favored product or the disfavored product. And so we have what is known as the order of stability of carbocations. So it turns out that a tertiary carbocation, all right, tertiary carbocation is a lot more stable, all right, a lot more stable than a secondary carbocation, which is more stable also a lot versus a primary carbocation over there. So we've got the secondary and the primary carbocation like that. And so we can use this fact to help us predict the regioselectivity of many different types of reactions where we are adding a strong acid like HI, HBr, or HCl to an alkene. Let's have a look. All right, so to wrap up this section, I want to mention that the reactions that we've been doing, so adding HCl, HBr, or HI to an alkene, are collectively known as hydrohalogenation. Why? Because we're adding an H, that's the hydro, and we're adding a halogen, typically an X like this, right? So it could be chlorine, bromine, or iodine that we're adding. So hydrohalogenation is the reaction. And when we do something like this, the typical pattern is that the proton goes to the least substituted position. All right, we've got the alkene. This one has got more carbons on it. This one's only got 2 carbon atoms on it over here. So it goes to the least substituted position because it would form the most stable carbocation. That's Markovnikov's rule. So the most stable carbocation would form over here, and the hydrogen goes to the least stable. That means that the halogen actually goes to the most substituted part of the alkene. So the major product of this would be something that looks like that over there. The minor product would look like this. So I'm putting the X in blue because it is actually the base. This was the acid, but this becomes the conjugate base, and a conjugate base is the same as the nucleophile in the reaction, okay? So the H is the first electrophile, and this is the first nucleophile, which adds its electrons to the H, forming the more stable carbocation, which is this one over here, all right, the tertiary carbocation. And then the remaining, I didn't show that break, that was very naughty. The remaining base that we have present, the conjugate base, which is either Cl minus, Br minus, or I minus, will add to the carbocation, forming our major product that looks like that. And that is the basic form of what is known as hydrohalogenation, the first reaction that we look at on alkenes.